The next concept we shall discuss is a collision in which rotation is involved. Consider this situation. On a smooth horizontal table, a rod is lying which is pivoted at one end. The pivot is frictionless and the rod is initially at rest. Now, as seen by you, it may appear as if the rod is hanging vertically downward, but you are seeing this from above a table. This is the top view. Okay, so the rod is actually horizontal, it's just lying on the table. And a particle whose mass is equal to that of the rod's mass is m, length is L, particle's mass is m, is moving towards one end of the rod with a velocity u directed perpendicular to the length of the rod. So as this particle moves forward and collides with the rod, we need to find out what is the angular velocity with which the rod begins to rotate. That is one part of the question. And the impulse exerted by force due to the pivot. That is the other part of the question. Now, to solve such problems, you need to be given some more information related to what kind of collision it is or what happens to one of the colliding objects after collision. Okay. So, in this problem, let us assume the particle comes to rest after collision. So, the particle collides with the rod and stops moving. The rod starts rotating due to the collision. The angular velocity with which it begins to rotate is what we need to calculate. Now, one common thing that happens in any collision is the transfer of momentum from one colliding body to another. And if the net force on the system is zero, the momentum lost by one object will be equal to momentum gained by the other. And in cases of collisions where rotation is involved, what happens is the transfer of angular momentum from one colliding body to the other. Okay. See, there will be a transfer of linear momentum as well. Whenever one object exerts a force on another object, some momentum transfer will definitely happen. But in cases where rotation is possible, you must consider the transfer of angular momentum also. And if the net torque acting on the system of colliding bodies is zero about any particular axis, then the angular momentum lost by one of the colliding bodies will be equal to the angular momentum gained by the other one. Okay. Principle of conservation of angular momentum. The net angular momentum of the system remains conserved. So let's see which of these principles is applicable in this situation. Now, when the particle goes and collides with the rod, okay, just before collision, the particle will be present here. It will exert a force on the rod. What force does the particle exert on the rod? Normal reaction or normal force. Let us indicate with a different color. On the rod, the normal force acts to the right. Okay, normal force from the name itself, normal being perpendicular to the surface of contact. Normal force has to act perpendicular to the length of the rod, and every action has equal and opposite reaction. The reaction force acts on the ball or the particle in this direction, and due to that reaction force, the particle comes to rest. Okay. So you must understand that the normal force here is causing a sudden disturbance in the motion of the particle and also the motion of the rod. Forces which do this, forces which cause a sudden disturbance in the motion of an object, are called impulsive forces. So the normal force here is an impulsive force. Fine. Now, how much ever normal force acts on the rod, the same amount of normal force acts on the particle as well. Therefore, the resultant of these two normal forces on the system is going to be zero. They're an action reaction pair. They won't contribute to the net force acting on the system. They won't even contribute to the net torque acting on the system about any axis. Okay. But when the particle goes and strikes the rod, does the pivot exert any force? We need to consider that possibility. And what other forces act on the system? The weights of the particle and the rod will be acting. Now you are looking at this from above the table. Okay. So weights will be acting perpendicular to the screen, vertically downward direction. And since weight is in the vertically downward direction, it has no component in the horizontal plane. So you don't have to consider weight of the rod or the particle to analyze this situation. Similarly, the table will be exerting a normal force on the rod as well as the particle. That normal force exerted by the table on the rod and particle will be in the upward direction. Those forces also need not be considered to analyze this situation because the normal forces which are acting perpendicular to the table won't have any component along the surface of the table. But the pivot may exert a force parallel to the surface of the table. Why? Now imagine this. I'm sure you all must have played pen fight in school with your friends. Some of you may be playing even now. So when you strike a pen at one end, okay, a pen which is lying freely on the table, you strike it at one end, you don't see the pen simply rotating about the other end like this. Okay, you find the pen rotating as well as translating. So the other end, okay, the end opposite to the one which you strike, also has a tendency to move. It may move up, it may move down. In some cases, it may not move also, based on how you are striking the pen exactly. So when the particle comes and strikes the rod, it is possible that this end of the rod has a tendency to get displaced, tendency to start moving. Then the pivot, okay, because of its nature, will have to prevent that motion of that end of the rod. So it's possible that the pivot also exerts a force in this case. Let us assume that end of the rod has a tendency to move in the forward direction. It is just an assumption. We don't know for sure in which direction it tends to move. Okay. Let's assume it has a tendency to move in the forward direction. Then in that case, the force exerted by the pivot, let's call it Fp, will be in the backward direction. Okay. In order to prevent the motion of that end of the rod. It could be in any direction depending on the direction in which the end of the rod has a tendency to move. Okay. Now, the normal forces acting on the rod and particle are an action-reaction pair. They don't contribute to net force, they don't contribute to net torque also. But the force exerted by the pivot becomes a net force on the rod plus particle, the colliding system. Okay. And if that force is non-zero, we don't know whether it is zero or non-zero. If that force is non-zero, it means there is a net force acting on this system. And if there is a net force acting on the system, we cannot apply linear momentum conservation. So since we are not sure whether the pivot exerts a force or not, we will not be applying linear momentum conservation to this system, and you will realize that it's not necessary also. Okay, and in fact, based on what we derive after this, we can tell whether the pivot actually exerted a force or not. We can even tell in which direction it exerted a force. Okay, let's see how all that can be done. So we are not going to be applying linear momentum conservation to this colliding system. Okay, what other principle should we try applying? Angular momentum conservation. Now, angular momentum of a system is conserved if the net torque on the system is zero. Now, these are the forces acting on the rod plus particle system in the plane of the table. To be able to apply angular momentum conservation, you need to first identify an axis about which the net torque is zero. Now, the normal forces here are an action-reaction pair. They will never produce a net non-zero torque about any axis. The only force you need to be bothered about is the force exerted by the pivot. Now we don't even know the proper direction in which the pivot exerts a force. We have just assumed it this way. But what we know for sure is the point of action of that force. It has to act at that end of the rod. Okay. So what we are going to do is we are going to consider an axis at that end of the rod. The axis will be perpendicular to the plane of the system, to the plane of the table. So it is basically a vertical axis. I'll mention that here. An axis which is perpendicular to the table. Now, why is it important to consider the orientation of the axis? See, these are the forces acting in the surface parallel to the surface of the table. But there are other forces also acting on this system. Their weights and normal forces from the table. Okay. Now, in this situation, they are balanced. Their weights and normal forces are balanced. But even if they are not balanced, the weight of the rod and the particle act perpendicular to the table, means they act parallel to this axis. Therefore, they cannot produce any torque. Okay, we are trying to check if the net torque about this axis is zero or not. Okay. So if you consider the weight of the rod and the weight of the particle also, since the lines of action of those forces are parallel to this axis, they cannot produce a torque about this axis. Similarly, the normal force acting on the rod from the table and the normal force acting on the on the particle from the table, they will also be parallel to this axis. They cannot produce a torque. So whether those forces are balanced or not, they are not going to produce any torque about this axis. Fine. Now, why did we choose the axis here? Because this axis passes through the point of action or point of application of the force exerted by the pivot. If the line of action of a force passes through an axis, that force cannot produce a torque about that axis. So a force exerted by the pivot cannot produce a torque about this axis. The normal forces, which are an action-reaction pair, also cannot produce a net torque about this axis. Individually, they can. Okay, the particle experiences a clockwise torque. The rod experiences an anti-clockwise torque about this axis. But the net torque, due to both these normal forces about this axis, is zero. Okay. Therefore, we have identified an axis about which the net torque on this rod plus particle system is zero. And now we will apply angular momentum conservation about that axis. How do we apply angular momentum conservation? Initial angular momentum of the system is equal to final angular momentum of the system about the same axis about which net torque is zero. You cannot take net torque about one axis to be zero and write angular momentum conservation about some other axis. Okay, fine. Before collision, the particle was moving with a velocity u in this direction. The mass of the particle is m and the rod was at rest. So initial angular momentum of this rod plus particle system is only the angular momentum of the particle. And how do we express angular momentum of a particle? The proper formula is m r cross v. But here we are only going to consider magnitude and then consider the direction separately. The formula for angular momentum of a particle is mvr perpendicular. Okay. Mass of the particle is m. The speed with which it is moving is v. In this case, we have considered it as u. And r perpendicular is the perpendicular distance from the axis about which you are trying to express the angular momentum to the line of action of velocity of the particle. Line of action of velocity is horizontal here. The perpendicular distance between the axis and the line of action of velocity of particle is the length of the rod itself. Therefore, the initial angular momentum of the particle is MUL about the axis that we have considered. And the rod did not have any initial angular momentum because rod was not moving initially. It was told to you that the particle comes to rest after collision. So after collision, the particle will not have any angular momentum because it is at rest. But the rod starts to rotate with an angular velocity omega and it will have angular momentum due to rotation. Now it executes rotation about a fixed axis, and for a rigid body rotating about a fixed axis, angular momentum about that axis is I omega. Moment of inertia of a rod about one end, about an axis passing through one end perpendicular to it is ml square by 3 multiplied with its angular velocity omega. So its final angular momentum, you can write it as ml square by 3 omega. So in this collision, conservation of linear momentum is not applicable. Conservation of angular momentum is applicable about this axis. Okay. So equating these two, we'll be able to derive the angular velocity with which the rod starts to rotate. Let us do that. Therefore, MUL, which was the total angular momentum of the system before collision, that is the angular momentum of the particle, is equal to ml square by 3 omega. Mass of the particle and rod were given to be equal, so they get cancelled. You get omega as 3u divided by L. This is the angular velocity with which the rod starts to rotate after the collision. Fine. Now there are some more things that we needed to find out in this problem. One of which was whether the pivot exerts any force or not. If yes, in which direction is it exerting the force? Let's see. The idea here to find out the direction in which the pivot exerts the force is to check what happens to the momentum of this system, because force disturbs the momentum of a system, right? So if you consider the particle plus rod as a system, had this force not acted on them, the momentum of the system would not have been disturbed. Okay? So if there is any disturbance in the momentum of this system happening, it has to happen due to this force. So what we are going to do is we are going to check the final linear momentum of this system and compare it with initial linear momentum of the system. If they are equal, that means momentum has not been disturbed. This force did not act during collision. Okay. If they are not equal, whatever disturbance occurred in the linear momentum of the system must have occurred due to this force. And the change in linear momentum becomes impulse. You can even tell how much is the impulse due to the force exerted by the pivot. Okay, let's do that. Initially, only the particle was moving, rod was not moving. Therefore, the total initial momentum of this system, that is the momentum before collision, is mu, mass of the particle, velocity of the particle, and momentum is a vector quantity, so mu I cap. That is the initial momentum of this system. Just after collision, according to the problem, the particle comes to rest. It's only the rod that is moving. Okay, so whatever linear momentum is left in the system must be in the rod. The rod is not executing translation; it is executing rotation. How do we express linear momentum of a rotating system? See, whether it's a translating system or a rotating system or a system which executes combined translation and rotation, okay, like the pen in a pen fight, linear momentum can always be expressed as mass of the system multiplied with the velocity of its center of mass. So we need to find out what is the velocity of center of mass of the rod just after collision. The center of mass of a uniformly distributed rod is its midpoint. The rod starts to rotate in the anti-clockwise sense. So center of mass of the rod will have a velocity in this direction, VCM, and it is going to execute circular motion about the axis of rotation of the rod. So since we know it is going to execute circular motion, we can easily express its velocity using V is equal to R omega. Okay, the velocity is anyway perpendicular to the position vector of the center of mass. Therefore, we can write this as L by 2 multiplied with omega. That's the velocity of center of mass of the rod. Why are we bothered about it? The rod is a rotating system. And to express the linear momentum of a rotating system, you need to multiply its mass with the velocity of its center of mass. So the final momentum of this particle plus rod system after the collision is mass of the rod multiplied with velocity of its center of mass, which is L by 2 omega. Now, how much was omega? We derived it as 3u by L. So, if you simplify this, the final momentum of the system turns out to be 3mu by 2. Okay, and what is the direction? The direction of velocity of center of mass, positive I cap. So, 3mu by 2 I cap, or you can write it as 1.5 mu I cap. Now, this is what is interesting. The initial momentum of the system was mu I cap before collision, and just after collision, it is 1.5 mu I cap. The momentum of this system is actually increasing after the collision, okay, or during the collision. The only source, okay, or the only cause of disturbance of momentum or change in momentum of this system is the force exerted by the pivot. Now, the calculation shows that the linear momentum of the system is increasing due to the collision. Momentum was to the right and it increases in the rightward direction. When is that possible? When the force acts in the rightward direction. Therefore, the direction we have assumed for force exerted by the pivot is incorrect. The calculation shows that momentum is increasing in the forward direction, means force must have acted in the forward direction, and the only force that can act on this system, only net force that can act on this system in the plane of the table is the force exerted by the pivot. Okay. Therefore, we can conclude that force exerted by the pivot is in this direction. How did we do that? Because, based on the fact that momentum in that direction is increasing, or the change in momentum is in the positive I cap direction. 1.5 mu I cap minus only mu I cap. The impulse here, which is basically the change in linear momentum of this system, can be calculated like this. Final linear momentum minus initial linear momentum, that is 0.5 mu I cap. This impulse was created by this force, the force exerted by the pivot. And whatever is the direction of impulse, same will be the direction of net force. So the force exerted by the pivot here is an impulsive force and it is creating an impulse of 0.5 mu on this system. And what is surprising is that the force acts to the right. Now, let us visualize the motion of this system. Now, usually in pen fight, what do you observe? When you flick one end of the pen, we see the pen rotating this way, and the other end appears to move forward. Okay? In most cases, it appears to move forward. Now, here the rod was struck at one end. Had the other end had a tendency to move forward, the pivot must have exerted a force in the backward direction. But actually, what is happening? The calculation is showing that the pivot exerted a force in the forward direction, and that is true. So, based on that, what can you conclude? You can conclude that when the rod is struck at one end, the other end of the rod actually has a tendency to move backward. That is why the force exerted by the pivot is in the forward direction to prevent the motion of that end of the rod. Okay. If you want to work further on this, you can consider different distances at which the particle strikes the rod and try to find out, like do the same analysis and try to find out the impulse exerted by the pivot. You will find that if the particle strikes the rod, okay, at a distance of L by 3 from the lower end, not low, I should not call it lower end, from the free end. Okay. If the particle strikes the rod at a distance L by 3 from the free end, you will find that the pivot does not exert any impulse at all. Okay. If the particle strikes the rod anywhere further away, okay, from the free end, the other end of the rod, the fixed end of the rod, will have a tendency to move forward and force exerted by the pivot will be in the backward direction. You can find out all those from the calculation that from a similar calculation. Okay. You assume the particle strikes at some distance, maybe L by 2 or something like that from the free end. Do the same analysis, do conservation of angular momentum, find out omega of the rod, then check the change, find out the change in the linear momentum. You will see that the impulse in that case will be in the backward direction. Okay, that's all for now. Thank you.